So, the following question was taken from the GDE External Prelim, Provincial Prelim from 2018, and it's question 9 on your worksheet. So, here we go. The following equation represents a reaction used to produce CO2 gas in a school laboratory. Pieces of calcium carbonate are added to a 0.1 mole per decimeter cubed hydrochloric acid solution in a glass beaker. So we got calcium carbonate, which is a solid, HCl, which is a solution, and the rest is my product. So we're dealing with rates of reaction. And then they say mention 3 ways to increase the rate of the CO2 production. You need to be very, very specific. So start at the beginning. We've got calcium carbonate as a solid, and they use pieces of calcium carbonate. So the very first thing I can do, so this is 9.1.1, is the first thing is I can use powdered calcium carbonate. Okay? Instead of large pieces. Okay, that's the first one. We also have an acid, which means it's going to have a concentration. All right, so we could increase the HCl concentration, and we can write it like that. The next two are fairly straightforward. We could heat the reaction mixture, increase the temperature. Okay. And of course, they only wanted 3, but there is a 4th one which you could say to me. Use a suitable catalyst. There we go. 4 options, they only needed 3. Discuss 2 methods to measure the rate of this reaction. And the big thing here is the fact that we're getting a gas. So either we need to measure the volume of the gas produced, or we need to measure the mass lost in an open container. Okay? They say discuss in science doesn't mean long paragraphs, okay? So let's talk about what happens when we measure the volume. So the first method we could do is we say that we would measure the rate. They're not actually asking me how I'm doing it. They just want to know what we're going to measure. So we would measure the rate of CO2 formed by measuring the volume produced per unit time. So I'm acknowledging that I'm forming a gas. The other one is the mass decreasing. So that's the first option. My second option is to measure, the rate at which the mass decreases. How? By placing the reaction vessel on a sensitive scale and recording the decrease in mass per unit time. okay? And that's, of course, going to give you the mass of the CO2 that escapes, okay? Next question. Give 2 reasons why this reaction will not reach equilibrium reach equilibrium in the beaker. Now, we haven't done equilibrium yet, but there's 2 reasons which you can just add in here. The one being it is an open system. It's not closed. The CO2 gas can escape. That will make more sense once we've done equilibrium. Okay. Now we get to the fun questions. They say, in an investigation, so this is now a different question. It's 9.2. In an investigation, different lengths of magnesium ribbon of the same width react with dilute hydrochloric acid of the same concentration. The rate at which hydrogen gas is produced in each reaction is measured, and the data recorded in the table below. So what we have here is the length of ribbon, and this is the rate per minute. So if we look at it, the longer the ribbon, the faster the rate. We get a bigger volume per minute. That's what we're saying here, okay? And here's the graph. Length of ribbon, rate of production, and you can see it's not quite a straight line, but it's a good enough line. Then they say use the graph to give the rate at which hydrogen gas is produced with a 5.5 centimeter length of ribbon. So we go into our graph. There's 5.5. Okay, so we're reading off the graph. 5.5 goes across to there. Oh, that's nice and easy. So 9.2.1. The rate is 5 centimeters cubed per minute. Oh, we like that question. Then, the experiment is repeated under the same conditions, except the hydrochloric acid is heated to 60 degrees before the ribbon is added. How will the gradient of the new graph differ from that of the original gradient? Well, if I increase the temperature, right, the reactions will go faster, okay? The reaction goes faster. If the reaction goes faster, then it must go at a steeper rate. So for 9.2, it's going to be a steeper gradient. They only wanted steeper, but that's okay. Then they said, explain your answer to question 9.2.2 in terms of the collision theory. Well, this one is, the official memo was a bit strange here, okay, in what they wanted. But because they said collision theory. So what you need to remember is, if we increase temperature, right, more particles have sufficient energy okay, therefore we have a greater number of effective collisions per unit time thus increasing the rate of reaction. The graph will then be steeper. Okay? What conclusion can be made? Now you need to be careful. We can see this is a straight line, but they have not drawn it through the origin. Okay? And if you look carefully, this actually isn't a line of best fit. Well, it's not great, okay? You cannot say it goes through the origin, because a rate of 0 when you have 0 length of magnesium ribbon, it's one of those things you just can't, you didn't take it all the way through. So what we can say, okay, is the rate of reaction increases as the length of the magnesium ribbon increases. I'm also hesitant to say it's directly proportional, because if I look at the length, look what happens here. This is at 2, length of 2, the rate is 2. At 4, the rate isn't 4. Okay, so when I doubled the length of the ribbon, I did not double the rate. That's the only way that we can say that they're directly proportional. All right, so just be very, very careful with that one. It looks almost directly proportional, but actually this won't go through the origin. So just be careful there for me. But that's the